In this video, I'll talk about the general linear least squares approach, which is basically a generalization of linear regression. After studying this video, you should be able to identify if a mathematical model is suitable for a linear least squares fit. You should be able to express that model as a linear combination of basis functions, if it is suitable. And we'll talk about what a basis function is in a minute. And then use MATLAB left division to implement the general linear least squares curve fitting approach. So here's the basic idea with general linear least squares. Many mathematical models can be written as a linear combination of functions. So recall that a linear combination just means it's some summation of some constant a sub I times some function f sub I of x would be a linear combination. Again, that's a summation sign of functions. So in this formulation, what we're going to do is consider a general linear model where we're going to have a mathematical model defined by y equals some a naught times z naught plus a1 z1, etc. So y is just equal to a summation of a sub I times z sub I, and the z's are called basis functions. So we'll have m plus 1 basis functions. And there's nothing special about the name basis function besides these functions are the basis for our curve fit. And they can be any function of the independent variable. So the data, we might have one or more independent variables. But an important note here is that the basis functions cannot contain any of the coefficients in the model, a naught, a1, etc. So recall for a linear regression, we were limited to models with two coefficients, right? So it had to be y is equal to some a0 plus a1x. And we can generalize that to this approach and call that y is equal to a0x raised to the 0 plus a1x, where our z0 is x to the 0 and z1 is just x, right? Because this equals 1. So we're just going to generalize that idea now, where as long as this is a linear combination of functions, or if it can be transformed into a linear combination of functions like we did those transformations in the last video, then we can use this general linear least squares approach for models that might have more than two constants. So let's see how that works. So here's some examples suitable for a general linear least squares approach. So one would be polynomials. So here we have, again, a z naught equal to 1, a z1 equal to x to the 1, a z2 equal x to the 2, etc. So a polynomial works as a linear combination of basis functions where each basis function is an increasing power of x. Another option could be a linear function of more than one variable. So again, here we have some constant here. Again, the basis function z0 equals 1. And now x1, that's just z1 equals x1, but now z2 is equal to x2. And we might have other independent variables. Say we have two or more independent variables in the problem. We'd have at least three constants for two independent variables, a0 plus an a1 and a2. Another example could be a decay model like we had for the parametric analysis early in the course. Note, in the case where the decay rates are known, we can formulate this as a general linear least squares model where z0 is equal to e to the k1x and z1 is equal to e to the k2x. And that's okay as long as k1 and k2 are known constants. If this model has four unknown constants, such that we have the case where we had A0, A1, A3, and A4, we actually couldn't formulate this as a linear least squares approach. You could try, say, taking the natural log to transform it. Natural log of y is equal to natural log of a naught e to the a1x plus a3e to the a4x, but that actually doesn't get us anywhere because we can't further simplify that natural log. And again, the problem here is we cannot have a z equal e to the a1x where this a1 is one of the model constants or parameters that we are seeking with the curve fit. So how about this one? Here's another example. Y equals a naught e to the a1x times the cosine of a3x. So we can try simplifying this a little bit, or try the natural log approach again to transform it. So we get natural log of y is equal to the natural log of a naught e to the a1x cosine a3x. And we can use that product rule for natural log. So this is equal to natural log of a0, which we could just define as some new constant, plus a1 times the natural log of x plus natural log of cosine a3x. So this one is okay. We could have a z naught. We can just redefine, it's just a constant, so we can just redefine that, and z naught equals 1. This one is okay. We could have a z1 equal to natural log of x, but this one is not an okay basis function because the constant is inside the function. So just beware of that when you're evaluating whether or not a mathematical model is suitable for this approach. So now that we've talked about how to find out if a model is suitable, let's look at how we implement the general linear least squares approach. So the first thing that we do is actually just plug the data points into the model equation. So if here's our general model equation, y model is equal to our linear combination of basis functions, we can get n linear combinations, and again, n is our number of data points that we're using for our curve fit, simply by plugging in the data points into this model. So we'll get yi plus a0 z0 plus, and this I would be the basis function z evaluated at the data point xi, and same with the rest of these basis functions. Now this isn't going to be an exact fit, so we've introduced some error, and that's going to be our residual of the ith data point. So we can write this in matrix form as y is equal to za plus e, and now we have a vector of residuals. And z is going to be a matrix of basis functions evaluated at our data points. So the first row would be all of our basis functions z evaluated at our first data point x1 on down to our last row where are our basis functions z evaluated at our last data point xn. So once we've done that, we've got this linear system for y. We can recognize that z is not going to be a square matrix. Since we're doing a curve fit, generally the number of data points is going to be greater than the number of model coefficients. One way to think about this is if we were doing a parabolic fit, then m would be equal to 2, and we would want to have n greater than 3 for a curve fit, because a parabola is uniquely defined by 3 points. So it's not really a least squares curve fit if we only have 3 points. That uniquely defines the parabola that passes through those 3 points. And that's actually more of an interpolation problem that we're going to talk about in the future. So we know that it's not square. It's actually an overdetermined matrix. But we can still use, recall that MATLAB left division can still work for an overdetermined matrix. So we'll just use left division. And if we use left division, what MATLAB's going to do, so we're just going to, in the case of this, we're just going to ignore that residuals vector and know that since we're using left division, MATLAB will go to that option where it uses the QR factorization routine, which again, it's beyond our scope in this class to get into the details of that routine, but conceptually what that routine does is it minimizes the least squares of the residuals. So it's a least squares fit, minimizing the sum of the squares of the residuals E. So hence the name linear least squares. So this is still a least squares fit, but we no longer call this a regression because it's not tied into the linear regression. Incidentally, QR factorization is the way that the polyfit function works. So it's always just going to basically formulate that matrix and then call left division and solve it with QR factorization. So let's look at an example implementing this in MATLAB. So here's a model for pressure and volume. It's a gas equation of state model. We want to determine the constants A1 and A2 in this equation of state. We know that gas constant R, and this is all at a temperature of 303 Kelvin. So we're going to use general linear least squares with left division. So the first thing that we need to do is define this. Now we'll formulate this for general linear least squares. So what I'm going to do to formulate this is just define y as equal to PV over RT minus 1. So recall we can still have a V that's okay in our Y in our model because we still have that implicit assumption of curve fitting that there's no air in the independent variable, in the independent data, or that the air in the independent data is much, much lower than the air in the dependent data. And then we need to bring the 1 over to the other side because we need to have a model constant before each basis function. So once we do that, we can rewrite this as y is equal to a1 times 1 over v, and that'll be our first basis function, plus a2 times 1 over v squared, and that'll be our second basis function. So this will be z0, and this will be z1. And that's what we see here. So here's the data. Here I'm just setting up our y value, and then using an anonymous function for each basis function, and building this matrix. So note, this matrix, we have 4 data points, so this is going to be a 4×2 system. It's overdetermined, but no problem there. Left division doesn't care that it's overdetermined. It just means it's going to use QR factorization to solve the system and do a least squares minimization of those residuals. And hence we're using left division to do this curve fit. So one other note, that's all there is to it to implement general linear least squares. Just coming back to this for a minute, it's all about setting up the problem so that you have y as some linear combination of basis functions, and then setting up your matrix of basis functions. Those are the two keys. After you do that, then you're just using left division. So a note on curve fit quality. Recall we talked about the standard error, and that equation was dependent on the number of degrees of freedom in the model. And for linear regression, that was always 2. And so we just had SR over N, where N is the number of data points, minus 2. But now we've kind of opened it up, so this can be any number of constants. And so we need to be mindful of that when we calculate the standard error, we always need to adjust whatever this value is for D in our calculation to be equal to the number of constants that we're determining through the curve fit. Now the coefficient of determination, that doesn't depend on the number of constants. That's still the same, ST minus SR over ST, where ST is the squared 2 norm of the model residuals, and ST is the squared 2 norm of the residuals with respect to the mean, and SR is the squared 2 norm with the residuals with respect to the model. And that concludes this video.